Welcome back. We have arrived at the last technical topic of this course of combustion in air breathing aero engines, and this topic is essentially combustion in scramjets. Now many people consider scramjet engines to be the future of high speed air propulsion, and it can be used for various purposes. But apart from that, the scramjet engines, there is an inherent beauty in the scramjet engines. It's conceptually very simple. Okay, there is no rotating machinery inside the scramjet engine as such. Air is compressed just by the design of the engine as such, just by reducing the cross sectional area. So when a high speed incoming air passes through a reducing cross sectional area, it automatically gets compressed by, and also there are some shock trains that is formed, and then you add heat onto this high pressure high speed air, and you can expand that subsequently to generate the thrust. Okay, so there is no compressor in a scramjet engine, there is no turbine in a scramjet engine. Okay, so because there is no turbine, there is no limitation of any, theoretically there is no such limitation on the maximum temperature that you have to on the maximum temperature that you can achieve in the combustion chamber, at least from a materials point of view. But despite this lack of limitations, lack of theoretical limitations, or this conceptual simplicity, technologically scramjets are very, very complex and scientifically very challenging, and that is what makes the whole thing, the design, analysis and experiment simulation in scramjet combustors and scramjet engines very, very challenging and exciting at the same time. Okay, so scramjets has been there for quite some time. It has been conceptualized more than 50 years ago, but still we do not have a commercially viable, commercially available scramjet engine which can take a load from one place to another. Okay, the reason is once again that despite this conceptual simplicity, scramjet engines pose enormous scientific and technological complexity. So here in this lecture on scramjet engines, we will just mainly focus on the combustion part of the scramjet engines, but we will get exposed to some of the complexities, because unlike in other engines, in the scramjet engine you cannot really talk about the combustor in isolation from the rest of the engine. So it's the full engine has to be essentially understood and treated as a whole to develop the insights for the processes that happens in a scramjet engine. So this is just this course will be just give you a very brief description and the important features. So first we will go into the introduction of the scramjets. Why do we need scramjet engines when we have rockets? Okay, we have rockets at very, very high Mach number, and it can go from all the way from the ground onto Moon, Mars, Venus, Neptune, anywhere across the solar system. Whereas the scramjets, of course, you know that these are air breathing engines, and as a result its transportation is restricted within the atmosphere. Okay, so why do we, despite the complexity and despite the challenges, why do people still want to develop scramjets when we have rockets? Okay, what is the reason? And then we will go into the steady 1D analysis of the engine a little bit. We will go into the essentially this Rayleigh flow, which is essentially a frictionless flow with heat addition, and we will see what happens when you add heat onto a high Mach number flow, and when the area of the flow path does not change. Okay, that creates some complexity. Then we will look into mixing. Of course, in scramjets mixing is a very, very big problem, and then we will look into flame stabilization. Flame stabilization is also a very big problem. We have looked into flame stabilization for an afterburner and for flame stabilization in subsonic flows, and we have seen the challenges. Basically we have seen that flame stabilization was inherently a problem of you have to ensure that you have sufficient chemical time scales for a given flow residence time scale, right. So the chemical time scales must always be shorter than the flow residence time scales for flame to be stabilized. But as you know, in a scramjet engine, the flow residence time scales are very short, because the scramjets typically operate at about Mach number like 6, 7 and higher. Okay, so the flow residence time is very short, so your stabilizing a flame in such a very high speed flow is extremely challenging, and this is one of the major challenges in a scramjet engine, that how do you ensure that the flame is stabilized at different conditions and of high Mach number flow. So here before we go into the scramjet engines, we need to take a look into something called a propulsion, a parameter that can quantify propulsion performance, and that parameter was sometimes called ISP, which is called the specific impulse, and if it is in units of seconds, it is essentially thrust per unit weight flow of propellants. Okay. Now the question is here is that what is a propellant? Now if you consider a turbofan or a turbofan engine, the propellant is only fuel. Okay. So it is essentially ISP, if I write it like this, is T divided by m dot mass flow rate of propellant times G. Okay. So that is why it's a weight flow of propellants. Okay. If it is so that's if ISP is in seconds, it is essentially thrust per unit weight flow of propellants. You can also define it as like a thrust per unit mass flow of propellants, but then the units will change. Okay. So to make it like weight flow, we have to multiply by this G. Now you see here we compare the different ISPs, the ISPs of different air breathing engines with that of a rocket. Okay. Now all air breathing engines essentially have higher ISP or higher specific impulse than that of a rocket, because in a rocket you are essentially carrying both the oxidizer as well as the fuel as the propellant. Okay. Whereas in these air breathing engines, your propellant that you need to carry is only the fuel. Okay. So immediately that gives rise to much higher ISPs for the or specific impulse for all these air breathing engines, and with respect to the rocket, and that is why you see at higher Mach number for ramjets and scramjets offer ISPs or specific impulse which is more than 2 times than that of a rocket at a Mach number from the range of like say 3.5 to 8, which is typically the regime of high speed propulsion. Okay. So this is the reason that because in a scramjet engine you need to carry only the fuel, okay, whereas the oxidizer is freely available from the air. Okay. The specific impulse of the scramjet engine is higher, of the order of about 1000, whereas in a rocket you have to carry both the oxidizer as well as the fuel. So for that reason the specific impulse of the rocket is inherently lower than that of any air breathing engine. Okay. But of course, as you see at very high Mach number, this approaches the that of the rocket when you as you go into like a higher and higher altitudes, you if you have to design an engine which goes into out of the atmosphere, then of course you need to carry the oxidizer. So then the ISP of that kind of a combined cycle scramjet will approach that of the rocket. Okay. So you see that when you consider the specific impulse, the turbofans are really very large, and then of course it reduces to ramjets and then to scramjets, but still the point is that the specific impulse of a ramjet is still more than a factor of 2 higher than that of a rocket. So you basically, with a given mass of fuel that you are carrying, okay, or the given mass flow rate of propellant or the given weight flow rate of propellant, you generate more thrust in a scramjet than you generate for a rocket. So economically scramjets, at least in theory, scramjets are much more a viable option for cruising, for long distance travel, or for cruising from one place to another, as opposed to that of a rocket. Okay. So, here you have again the specific impulse, but you see that the specific impulse also depends on the fuel, because the amount of energy that is available depends on the fuel type. Okay. So, if it is like the hydrogen based fuel, you see this X43A, which was the plane which is a scramjet engine, test engine developed by NASA, that has a higher ISP than compared to X51, which was based on the hydrocarbon fuel, and which was also tested in this decade. Okay. So, the advantage of hydrogen fuel is that it can have a cryogenic storage, it has a larger volume, it is it's easy to ignite. Hydrogen is very easy to ignite, it has a huge flammability limit both in the lean side as well as the rich side. Whereas, if you want to use hydrocarbon fuel, of course, it is easy to handle, and it has for a given volume you get much more energy. So, you can have a smaller fuel tank, but of course, it is much harder to ignite, and it has other processes like it has to be if you are using liquid fuel directly into the scramjet, it has to first the liquid jet has to break up, it has to atomize, it has the liquid droplets has to evaporate, so on and so forth. So, that requires some additional time. But typically, if it is a specific impulse, then the scramjets with hydrogen fuels are better than scramjets for with hydrocarbon fuels. But practically, because air breathing engines are so popular because of the high energy density of the hydrocarbon fuel. Okay, and because we have essentially mastered the ability to carry liquid hydrocarbon fuel, and once all these problems are settled, of course, this type of liquid hydrocarbon based scramjet engines could emerge as the hypersonic engine of choice, both for even for commercial aviation in the long term future. Okay. So, that is why it is important to know about scramjet engines and how do they operate. So, here is a difference between scramjets and ramjets engines. Now, in principle they are kind of similar, that is, you compress the air by ramming it into the engine. So, scramjets are nothing but supersonic combustion ramjets. Okay. So, in the ramjet what happens is that, so you have the inlet. Okay, and then you have a so the as it passes through the inlet, so the air is essentially slowed down. It's because the inlet air that comes into the engine is supersonic. So, with a converging, if you design a converging cross section or the converging flow path, then of course the air would essentially slow down into the inside the engine, and when the subsonic and so we are talking about in this slide we are comparing between subsonic and supersonic combustion ramjets. Now, scramjets, which are essentially the supersonic combustion ramjets and normal ramjets, they work on the similar principle, that is they do not have a compressor or any rotating machinery to compress the air. So, in this case the incoming air is compressed by the ramming action of the air into the engine, and that ramming action is created by designing by ramming the supersonic air into a converging flow path, that is how the inlet is designed, as you see here. So, the supersonic air comes, it passes through an area which is reducing, and because the flow is supersonic, instead of accelerating, it slows down and the pressure increases. Okay. And then of course, you have the diffuser and then you have the burner. So, in the ramjet, by the time it enters into the burner, okay, the series of shock trains, even if there might be a normal shock also, have reduced the Mach number to less than 1. Okay. So, as you know, the downstream of a normal shock, the flow is always subsonic. So, if there is a normal shock formed anywhere inside this engine, so the flow downstream of that is invariably subsonic. So, in a ramjet, so this is essentially a ramjet. In a ramjet, this series of shock trains ensure that the incoming supersonic air is transformed into subsonic flow by the time it enters into the burner. So then in the burner you can have this struts etc., and you can have flame stabilization similar to what you have in the afterburner, and then you can but still the flow is of course subsonic, and then you can expand it through a convergent divergent nozzle to generate a fast exhaust, and which can generate large thrust. Okay. So this is the ramjet. In comparison, in the scramjet, which is the supersonic combustion ramjet, as the name suggests, the combustion happens in supersonic flow. Okay. So it will be apparent why it is so. So as such, this is in here the Mach number of the incoming air is even much greater than 1. Okay. It is of the order of 6, 7 for an efficient operation of a scramjet. So here you design, again it passes through the inlet, it is compressed, but it is compressed in such a manner that there is no normal shock formed anywhere inside the engine. Okay. So it is compressed, and then it again passes through the diffuser. There is a series of oblique shock trains that is being formed, of course, and the pressure rises through these things as the flow passes through these shock trains, and passes through this convergent cross section. By the time it enters into the burner, it still remains supersonic because there is no normal shock formed, and the scramjet is designed in such a manner that the flow remains supersonic by the time it enters into the combustor. So here also you can have different modes of flame stabilization, and then it passes through the nozzle where the flow is further expanded, and the flow becomes Mach number becomes larger, and then it can be exhausted to generate the required thrust. Okay. So this is the difference between subsonic and supersonic combustion ramjets, or difference between ramjets and scramjets. That is, the flow inside the burner in the ramjet is less than 1, the flow inside the burner in the scramjet is greater than 1. Now why it is so? Why do we need to have supersonic combustion for high Mach number flights? Okay. So as you see here, the ramjets are, that is, for combustion happening in subsonic flows, that kind of an engine is only suitable for a limited Mach number of, say, Mach number from 3 to 6 approximately, whereas scramjets are suitable for Mach number from about 6 to 14, theoretically at least. Okay. Or for hydrocarbon fuels it is from Mach number say 6 to 9. Okay. Why it is so? Why can't we have subsonic combustion for high Mach number flights? By the way, I mean you can have, the reason is that there is nothing that prevents having combustion in a ramjet mode, that is in a subsonic mode in a Mach 12 flight, but then the point is that what will happen? Okay. What will happen is compared here. So let us consider a Mach 12 flight, okay, and your combustion chamber, and the entry into the combustion chamber can be either supersonic or subsonic. Okay. So here in both the cases, so this is essentially a scramjet, this is essentially a ramjet. Okay. And this is once again, this is a scramjet. And this is a ramjet. So ratio of burner entrance to capture area, these are same in both cases. Okay. Stagnation pressure recovery. Okay. Stagnation pressure recovery, the PT, the P0 inside the stagnation chamber, inside the stagnation the P0 inside the combustion chamber divided by P0 at the inlet, that is can be defined as a stagnation pressure recovery, and in a scramjet that is much higher, 0.5. Of course here it is much lower because you have a normal shock formed and there are entropic losses which is much higher in the ramjet, and it will be very, very small. So the stagnation pressure recovery would be very small. The pressure here is 2.7, here is 75, enormous pressure rise. Okay. So if you are compressing a Mach 12 flight, a Mach 12 air into a subsonic air, the pressure rise would be enormous. So you have to design, it will be very difficult to design a combustor for such a high speed operation which can have 75 atmosphere. Temperature, this is the key. You see the combustor entry temperature in a scramjet if you are slowing down a Mach 12 flight, Mach 12 air that is entering into your engine at the inlet into say Mach 2 at the combustor entry, or here it is Mach 4.9 at the combustor entry, the temperature would be 1250 Kelvin. Whereas in this case, if you are reducing a Mach 12, if you are decelerating a Mach 12 air to Mach 0.33 air at the entry of the combustion chamber in the ramjet, the temperature, the static temperature at the entry of the combustion chamber would be 4500 Kelvin. Why would you need even combustion? How much increase in temperature can we achieve when the incoming air is itself 4500 Kelvin? And the problem is that even if you do combustion in the 4500 Kelvin, it will be instead of adding heat, it will essentially absorb heat, because the dissociation reactions would dominate at such very high temperature. Everything would dissociate, air would dissociate also, and heat would be absorbed to perform those dissociation reactions. So it will be essentially counterproductive to even add heat. But of course, you cannot have without adding heat, you cannot complete the circle and you cannot generate thrust. So thermodynamics will prevent that you can generate any thrust from such an engine. So it will be like compression, you will only compress the air from very high Mach number flow to very high temperature air, and then you will release the same without generating any net thrust. Okay. So that will be the effect. So you cannot generate thrust if you are essentially working in a ramjet mode for a Mach 12 flight, of course. Okay. And of course, at a Mach 12 flight you cannot have any compressors or a turbine, because compressors, as you know, cannot operate at Mach 12 because of the very strong shocks that will form. Okay. So you see, this is the reason why ramjets cannot operate, that is combustion cannot, and because of the dissociation reactions essentially, and the fact that your added enthalpy, even if there is no dissociation reaction, that enthalpy that you can add to the flow by combustion is minuscule compared to the enthalpy that is already present in the flow, in this flow. Okay. In terms of the, at least in terms of at least in terms of the thermal energy. So you cannot really add much of thermal energy into the flow when you are operating a ramjet, when you are operating your engine in a ramjet mode for a Mach 12 flight. Okay. So you have to have combustion in supersonic flow if you are operating at a high Mach number limit. Okay. So this is, but then it poses big challenge, that supersonic combustion is not easy to achieve, because the fact that if your flow is supersonic at the entry of the combustion chamber, Mach 4.9, forget Mach 4.9, even if it is Mach 2, you will find that it has a flow velocity of the order of like about 1 kilometers per second. Okay. To have combustion sustained in such a flow is extremely challenging, and we need the best of combustion knowledge and design to ensure that we can have a stabilized flame at this high Mach number. So this is the reason that if you are compressing a high Mach number flow to subsonic, and decelerating if you are decelerating a high Mach number flow to subsonic flow, then the temperature rise would be so enormous that you cannot really add much of thermal energy into that high temperature flow, and even if you add, it will be counterproductive, because all the dissociation reactions will dominate, and essentially the energy added by combustion will be used up in satisfying those, in performing those dissociation reactions. So there will be no energy left for essentially expanding the flow. So the only option is to, if you want to operate a Mach 12 engine, is that you have to work in a scramjet mode where your combustion must happen in supersonic air. Okay. So, this is the scramjet engine as you see. The shock angles will be quite narrow, and that calls for this this very sharp cone at the inlet. So, this part will be essentially you will see that the shocks will form like this, okay, and this part will essentially will also compress the airflow, and this will be this part will be characterized by external compression. So, the air essentially enters into becomes an internal flow at this part where there will be internal compression. So, and there will be this shock trains being formed, this oblique shock waves being formed, and then you have kind of a constant area duct which is called an isolator to contain this pre-combustion shock train, and then there will be you will add essentially the fuel in this part, okay. So, you will add fuel into this part, and the fuel will burn, and you have to ensure that you basically increase the cross sectional area to prevent something called thermal choking, and then you increase the cross section area slightly, and then you expand the flow by providing a very large diverging duct to essentially accelerate the flow, which will generate the required thrust. Okay. So, as you see that what I was saying is that this conceptually it is very simple, right. It is just a variable cross sectional area duct, okay. And of course, then there are like different kind of angles, but because you see that because there is no such rotating machinery, it's the flow is very hard to control in this kind of thing. So, the design needs to be immaculate to ensure the perfect performance of a scramjet engine. And the other thing is that you see that yes, we call this portion combustor, but the combustor is essentially very intricately related to the inlet, to this inlet where we have external compression of the external flow, where you have internal compression, and then you have the isolator, and then you have the nozzle. So, the whole thing becomes very coupled, and because there is no such controlling machinery, rotating machinery which can be controlled at the order of the operator, the combustor also encounters a wide variety of flow and thermodynamic conditions. So, another challenge in the scramjet engine is that because you cannot really control all this flows here through different kind of machinery, your combustor must be designed in such a manner that it must be able to encounter a wide variety of flow parameters and thermodynamic parameters. So, that makes also the scramjet engine design and operation and analysis very challenging. So, to summarize, the scramjet propulsion system is a hypersonic air breathing engine in which heat addition due to combustion of fuel and air occurs in a flow that is supersonic relative to the engine. So, that is the hallmark of a scramjet engine, that the flow in the combustor is supersonic. Okay. In a ramjet engine, the combustion happens in subsonic air. Okay. So, once again I repeat, the scramjet engine is characterized by conceptual simplicity, but very high scientific and technological complexity. Okay. So, what are the processes, okay, and what are the typical numbers that one can expect in a scramjet engine? So, before we go into the numbers, let us describe the process. So, you see that at this nose you have this bow shock being formed, large bow shock, and there can be some non-equilibrium effects here, and then the flow will essentially flow from a boundary layer along this engine, and even there can be a large boundary layer developing, and that boundary layer can transition from laminar to turbulence, and then the boundary layer even becomes more thicker. And of course, the larger boundary layer this leads to increased drag, which you do not want. So, there can be might be necessary to bleed off some part of the boundary layer. Okay. And then you again have this different internal at this you have a different kind of shocks forming, but oblique shocks, no normal shock can be formed in the scramjet engine, because then the flow will transition to subsonic. And then of course as once again this boundary layer develops, you see that you have a shock boundary layer interaction. So as soon as that happens, there is chance for the boundary layer to separate, because as you know the pressure increases across a shock. And so the what happens is that the boundary layer sees, and across the shock the boundary layer sees an increased pressure, which is essentially an adverse pressure gradient. And as you know, when there is an adverse pressure gradient, the boundary layer separates. So there can be copious boundary layer separation also, so one needs to control that. You really don't want boundary layer separation. Okay. And then of course you have this after the external inlet and after the internal inlet, you can have an isolator. I'll come to the isolator, and which contains essentially the shock train. And then you have this combustor. The combustor is essentially it comprises of the fuel injection system, where you are injecting the fuel, and it can have a flame stabilization system. Of course you have to ensure that before you have the between the fuel injection system and before you encounter the flame stabilization system, there has to be intricate fuel air mixing, because only then combustion can happen. So this combustor essentially will have to accommodate the atomization, evaporation, if you are using a liquid fuel, and then you have to accommodate mixing, and then you have ignition, combustion, all these things. Okay. And then we have this large expanded nozzle which accelerates the flow further. Now you have seen that in a gas turbine combustor, okay, in a gas turbine combustor, because the flow into the combustor was subsonic, and because of course gas turbine combustors the flows are subsonic, and because you are adding heat into that subsonic flow, there was a small pressure drop that you have learnt always. But here you are adding heat into a supersonic flow. Okay. So when you add heat into a supersonic flow, and if the cross sectional area is constant, then you have pressure rise. Okay. Now when you have pressure rise, what happens? Of course you cannot, the flow does not want to go into a region where the pressure is increasing. Okay. It is the negative pressure gradient that is the force that drives the flow. Okay. But of course the flow can proceed due to its own inertia, but it does not really want to go. So what happens is that in this supersonic flow, that is reflected in form of a shock waves can be formed, and there can lead to kind of different kind of oscillations. Okay. So but you do not want these oscillations, this pressure rise, which is the pressure is rising in the combustor. So if I plot the pressure rise only in this combustor part, it will be something like this. Okay. So you do not want this flow to sense this pressure rise, despite the fact that it is a supersonic flow. But if it somehow this pressure rise reduces the mass flow rate too much, then there is a possibility that there can even be a normal shock being formed in this inlet, and of course then the whole flow becomes subsonic and your scramjet combustor is lost. Okay. And the whole thing is essentially breaks down, then becomes the flow becomes so subsonic, the temperature rises. So you really cannot afford that. Okay. And this, before even that normal shock forms, there is a lot of things in oscillations can happen, which is called essentially unstart inside the inlet and the isolator. So you really do not want that. So to prevent that, what you have is that you design a constant cross section called this isolator, the purpose of which is essential to contain the shock train and to essentially shield the inlet. Okay. This isolator essentially this shields the inlet from the adverse effects of pressure rise in the combustor. Okay. So this is the it's really, otherwise it's adds to drag and all these things, but this is the thing that it purpose serves. So all of the parts are very easy to understand. The inlet of course is for the ramming action, where you are designing this reducing cross section so that your flow, essentially the supersonic flow essentially slows down and the pressure increases, because you, to complete the thermodynamic cycle and to extract work or to generate thrust, you need to add heat only at high pressure. So this part causes the pressure rise, okay. This part causes the pressure rise. This isolated part essentially shields the inlet from the adverse effects of pressure rise in the combustor, and then in the combustor you add heat, but before that you also add fuel and allow the fuel to mix, and then the fuel can get burnt, and then increase the stagnation enthalpy of the flow, and then this very high stagnation enthalpy flow can be essentially accelerated further in this in this divergent nozzle to generate large thrust. So what are the numbers that we are talking about? So typical scramjet can operate at Mach number 6. And if we look into the numbers that we are interested for the typical scramjet operation, so it is let us consider this scramjet engine flying at a altitude of 30 km at Mach number 6. So the static pressure it can encounter is about 1.2 kilopascal, and the static temperature can be about 226 Kelvin. Of course, it is reduced because of the high altitude, okay. And the total temperature is essentially T static plus V square by 2 Cp, okay. So this total temperature is about 1853 Kelvin. Now these are approximate numbers which come out from this for a typical for a scramjet engine. And of course the total temperature can remain fixed throughout the engine, but the total pressure of course should reduce because of entropy rise due to friction, etc., and shock waves, etc. So by the time it enters into the isolator, so if we can consider even the isolator to be part of the combustor, if it is in a ramjet mode, then of course the Mach number should be small. The Mach number is about 0.3, and the static temperature should rise very much, 1700 Kelvin, which is, you see, that enormously large to for adding substantial amount of heat. Total temperature still remains same, okay. So whereas in the scramjet mode you can have a Mach number of which should be supersonic, so the Mach number is 2.2, whereas you see the static temperature is now good, it is about 1000 Kelvin, whereas the total temperature can be reduced because of the boundary layer bleed, etc. Okay. So but it of course remains very same, close to that, okay. So now these are the typical numbers. So you see that why this scramjet mode of operation is preferred, because the static temperature that of the flow that enters into the combustor is at much lower temperature, and there is room to add heat into the flow, okay, without incurring or without inducing strong dissociation reactions. You can add heat into 1000 Kelvin and take it to say 2200 Kelvin, okay. But what will you do at adding heat into this into this flow? There is nothing. So this is once again the typical schematic that we were discussing. If we and this is also the cycle corresponding to this. So if this is 0 is the free stream conditions and 1 is the beginning of compression. So this part is essentially the compression that happens, external plus internal compression is combined, and then at 2.1 it enters into the isolator, at 3 it enters into the combustor, at 4 it this combustion chamber exit, and then it at 10 from there it's essentially the nozzle. So this is essentially the inlet or the intake, and this is the nozzle, and this is your isolator, and this part is your combustor, okay. So, in the enthalpy entropy diagram, you see that of course, this type of compression through shock waves, through different kind of oblique shock waves induces entropy rise, entropy is generated. So, from the ideal cycle it deviates 2.1 and then it goes to 3, and then you see combustion we still consider for the purpose of the cycle, we can consider at constant pressure, just like in a gas turbine engine we consider that pressure drops slightly, but actually you will see that here the combustion, the pressure rises substantially, it cannot be really neglected, and then it has an expansion process through the nozzle. So, typically if you have if your inlet Mach number is m0 and your combustion chamber entrance Mach number is m3, then this relation typically holds, and it's essentially been shown that essentially it's for large Mach number limit for large m0 is essentially T0 by T3, and T0 by T3 is of the order of 10. So, this m3 by m0 essentially becomes the square root of essentially 3.33, something like that. So, you see here if this Mach number is 6, this becomes a Mach number of 2 or something like that. Okay. So, this is the thing that for a vehicle which is flying at a Mach of 6, the combustor entry Mach number of course reduces, but it is still supersonic. Okay. So, even if the flight Mach number is 6, your Mach number at the combustor entry is 2.2, but the only thing that remains constant is essentially the total temperature, the stagnation temperature, but the static temperature increases because of the compression action, and now you have to add, you have to consider this combustor. So, this is the scramjet, how the combustor is essentially integrated into the scramjet engine, and these are the basic operations of the scramjet engine. So, in the next part we will take up how we can add what happens when we add heat into a supersonic flow, and it is a very fundamental thing, but we will still do the analysis because this is a little bit counterintuitive. We are so far in the course we have never discussed what happens to the flow when you add heat into it. So, we will discuss that, and we will move forward with the different processes that happens in a scramjet engine. So, thank you.